Hi, Mike. Can you hear me?
I can hear you. Are you the MC for this session?
I suspect that the audio only works within the online people and it's not working in the room. Can you hear me, Mike?
I'm gonna check. There it is.
So you were muted.
That's the issue. All right, so we're good now, and we're really hot. Let's see where we're at. This is.
I can bring you down here if you like.
Let me check. Let me make sure this was set to line. Check. Yeah, that's helpful. Okay. All right. Can you hear us on the presenter end? We should be actually
Two.
Yeah, we should be sending. Hello. Make sure those are AB. Yeah. Check. Yeah, we're definitely sending. Andy, can you hear us? Andy, are you there? Hey, Andy, are you there? You hear us okay? Good morning, Andy. Good morning. We're not sending me out?
Not that it matters. Well, we must be.
Yeah, it's coming here. So routing check, and it's Yeah, it's definitely going into vMix. And it won't affect. Hey, Dylan, can you hear us? Okay.
Tell him to unmute his mic.
Can you unmute your mic and talk to us?
Testing, testing. 1, 2, 3.
Sounds great.
Sounds like you can hear me.
We can. Okay.
You want me to mute again?
I guess. I don't know. I don't. You may not have, but we're getting it. We're good.
I'm getting a slight echo, but I think it's because the speakers are projecting into the microphone from where you're sitting. So I think we're okay.
Yeah, I think you're right. I think that's exactly what's happening.
But
What would you like
it's
to
not.
see, Tim?
I think you're totally fine. I don't think you need to worry about it. It's just
True.
where the mic is right
True.
now.
It is, and we're out at front of house, so we're going to hear everything in the house as well. All right, I'm shutting down.
Okay, me too.
We are going to where? Herbert? Herbert.
2, 2, 2. 1, 2. Testing 1, 2. 2, 2. Two, 2. Testing. 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 Testing 1, 2. 1, 2. Two, 2.
Morning, thanks. Did your frequencies get switched to Pablo's new plan?
No. He texted that, didn't he, right?
Yeah.
I just took some fresh batteries from your stores just to put them in for the day.
That's why they're there.
Hey, Mike. You actually hear me?
I can hear you fine. This is Arndt.
Awesome. Cool. I can see myself in the picture there. Yeah, testing 1, 2, 3. Can everybody hear me there in Dublin? Testing. Testing some more. We're going to talk about High-mem. From beautiful, dark, but sunny California. Awesome.
2, 2, 2, 2, 2, 2. Two. Two, 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 two. Test, test, test. 2, 2. Testing.
I can hear you.
So Christian, you'll be responsible to sort this out. You want to do kernel sort. Trained yesterday. All right. Do you hear me?
Yes.
Ira?
Yep, I can hear you. Morning.
Great. So this is the first in-person installment of LoongArch microconference. We are trying to make different architecture people to talk with each other. They don't usually. And there are lots of things that implemented differently in different architectures for no apparent reason. So one of them is high memory. Ira will be talking about it in a bit. We have a remote co-runner of the conference, Arnd, who also helped with the organization and everything. Arnd, can you show yourself on the screen for a second, please? Probably not. Now, for the remote presenters, we ask not to close the room, please. So if you are leaving the presentation, there is a button leave, or just close your browser window because restarting the room is taking too much time. And now I'm giving the presenter to Ira, and I think I'll close the chat so we'll get a better picture. Ira, it's all yours.
All right. Well, good morning and welcome. Do I need to? Okay, I'm going to bring up my presentation here. All right. Well, good morning. I'm going to talk about some of the High-mem API stuff that we're working on and discuss a little bit about what the future holds, or maybe get a discussion started. As Mike said, it is interesting, all the different architectures that are out there. I happen to work for Intel, but I've also done work on PowerPC in the past within Linux. So I'm familiar with the fact that Linux supports many different architectures, and that's part of what this community should be striving for. Oh, let me see. Do I have to click down here? Okay. So just a quick review for anybody in the room who's not familiar with High-mem. It's possible that everybody here already knows this, but High-mem is designed for 32-bit kernels running on 32-bit machines with large amounts of memory. The kernel only maps higher mem pages as they're needed. So the idea came about long in the past, long before I ever was working on this part of the kernel, to be able to use this additional memory beyond what the kernel could directly map beyond the 1 gig space by default. Obviously, that can be configured differently, but and then effectively, a lot of user space apps could use this additional memory, and then the kernel just maps it. So that interface, that High-mem interface, became known as the Kmap interface. So some might be wondering why I'm working on this. Sometimes I wonder why I'm working on this, but that's okay. So about almost maybe 2 years ago now, maybe it was a year and a half, I started working on a feature within Intel called Protection Key Supervisor. So some people may be familiar with user space P keys that are already in the kernel and upstream that allow an additional overlay of protections beyond what the page table protections, the default read-write page table protections that are available. And when I started working on this, I was doing this additional, ARM brings up a good thing. Large amounts is still under 4 gig, right? But it's more like 768 megabytes, right? Yes. So PAE is additional address space beyond what the 32 bits could do. So, High-mem can be used for either just a 32-bit machine or a PAE machine. PAE can map additional, up to 8 gigs or more. I'm just reading the chat here, sorry. So the protection keys that I was working on did additional overlay protections on kernel mappings. And this was a thread local CPU protection. And one of our use cases, and this is a really quick way to change permissions on massive amounts of page tables, massive amount of pages rather, I'm sorry, without doing TLB flushes. It's a really slick feature. But one of our use cases that I was striving for was something called persistent memory stray write protection. And for those of you who don't know, persistent memory can map a large amount of space. And we were basically abusing the Kmap interface to get users within the kernel to be able to turn on and off these protections within the kernel without having to modify every file system or any driver that was potentially mapping a persistent memory page. And so I kind of fell into this working on the Kmap subsystem, which is the High-mem subsystem, and figuring out what to do there. And so my use case was actually focused on 64-bit kernels and 64-bit machines and using this Kmap interface and kind of modifying it. But, then it became kind of a, well, do we really need High-mem anymore, etc. So I'm going to kind of present that. So that's kind of how I came into this. and why I'm working on it. So these were the issues that I was running into. Page address, which is typically what the kernel uses to get an address of a page. This is a function from way back. Basically, you have a page and you want to get the virtual address to that page. By default, this is very fast because it's just a mathematical lookup because the kernel maintains all of its accessible memory in the direct map. But page address has no corresponding unmap function or corresponding, map, unmap, or in PKS's case, no corresponding unprotect, protect call. So page address was not going to be able to work for us. And like I said in the previous slide, I kind of fell into this by saying, hey, well, we can just use Kmap because Kmap has a mapping and an unmap function. And Kmap Atomic has a mapping and an unmap function. But we had another issue with PKS and Kmap, which is that Kmap itself, the actual function Kmap, creates a mapping within the kernel, but that virtual address mapping can then actually be used by any thread in the kernel as long as that mapping exists. So it was a global mapping for the kernel. It wasn't really designed that way originally, but it was the easiest way to make the implementation at the time. So because PKS was thread local, I couldn't use Kmap. So I was starting to develop a new interface called Kmap Local, or Kmap Thread, actually, is what I called it originally. And that led to some discussions on the mailing list, and Thomas Gleixner actually created Kmap Local page. And what this did was create a local mapping within a single thread, hence the local page call. And he developed it in such a way that it could actually replace Kmap and Kmap Atomic. So fast forward a little bit as we're going along, and effectively where we stand right now is that Kmap and Kmap Atomic, those actual calls are deprecated, even on 32-bit. And this kind of gets into where, I'm starting to modify the APIs to High-mem. So the other thing about page address and Kmap is, as I was getting into this, they're just confusing. A lot of driver writers, they'll call Kmap because they know it's safe. But, well, do I call Kmap? Do I call Kmap Atomic? Well, now I got this Kmap local page. So, like, all these different calls. And then, some people jump in and say, well, just use page address. And so this kind of just confuses everything about, why do these calls exist? Some people also say, as we move into a world where 32-bit machines and 32-bit kernels are much more prevalent, a lot of people just kind of say, why do I need this at all? So that, that's more of what this presentation is about too, is, what do we do going forward? So as I was working on this, Mike also has been working on things to, hide parts of the memory from the direct map. And so PKS isn't kind of the first user who wants to have a more structured organization and more structured access to the direct map, even on 64-bit kernels. So we kind of have this overlapping, like I mentioned before, we have this overlapping between this new use case and this new need for something even in 64-bit, and kind of merging it into this existing interface, which is applicable to 32-bit. So Kmap local page, a little bit more details about it. It can be used in any context. It disables migration, but not preemption. So it effectively, it will keep your mapping and that thread on that CPU because it actually uses some CPU local and it it's not just CPU local. It stores some stuff in the struct thread to be able to, create some mappings. If the thread does get preempted, it will restore those mappings for you. So, it's a much nicer function. It's because it can be used in any context, it can be replaced. It can replace Kmap Atomic pretty much anywhere. Unfortunately, the Kmap calls need to be evaluated because, like I said, the Kmap calls kind of introduce this additional feature, if you will, that the mappings can be used on any thread. And that's not really the way Kmap was designed, because Kmap and the High-mem interface was really to do a temporary mapping of these High-mem pages, so the kernel could do a quick access to that memory, you know, say a user space page is being written or something like that, and then let it go. Because again, by definition, the High-mem interface was designed for 32-bit kernels that, you know, really wanted to, you know, the low mem resources were I've forgotten the word I'm trying to say, scarce. All right, so this kind of since I presented some stuff at LSF, you know, we've discussed a little bit more about, well, do we even need High-mem? And Arn has actually written a great article about this. So I'm not really going to try to present this in particular, but I think some of the discussion that we could have today is, you know, what is the need for large memory on, you know, 32-bit architectures? You know, we've already had some discussions on the mailing list and some email discussions that it's very clear that we still need High-mem today and possibly for a while into the future. But some of the discussions that we've had also center around, and I throw out the question also about how many cores are going to be in these smaller systems. I think really at this point, most 32-bit architectures that are running with large amounts of memory are some form of embedded board or some form of embedded system. So my gut says that those aren't going to be large core counts, but you know, even your Android phone has 8 cores. I think some may be pushing 16. So, and the reason I asked that is this Kmap local page, you know, because it has some resources associated that are per thread, they're per core, that could push into the limits of what Kmap local page can do. So, you know, that kind of factors in. I don't think it's really critical at this point. But my gut says that any system that needs, that is still 32-bit but has large amounts of memory is probably also not going to have a lot of number of cores. You know, 8 or 16 is fine, but you know, so I don't really know what people, if people have any feedback on that. So anyway, something to think about. I don't know if anybody wants to speak up, and feel free to interrupt me, questions with chat or whatever. I see Arn is typing something.
Yeah, I can just talk here. So on ARM, we have very few 32-bit machines with 16 cores. Realistically, anything except for the Axia is up to 4 cores only. And on MIPS, I think the maximum that is affected would be a 2-core machine.
Cool. That kind of goes again.
Yeah, PowerPC, there might actually be some more. I can look it up quickly and type it in the chat.
Okay. Yeah, that kind of goes with what my gut feeling was. Like I said earlier, I kind of fell into this work. You know, I really like the fact that Linux is supported on multiple architectures. And, you know, I love supporting that, but it's not an area that I'm super familiar with. So, you know, hopefully I can research and be, you know, hopefully I can help with this community, but, you know, it's just, there's so many different architectures and there's so many different, especially when you get into these embedded boards, some of them are so specific. Anyway, so I think that as a community, we can get through this, but, you know, I'm by far not the expert in this area. So the next question becomes more of a software question, not so much about Okay, 8 cores. Yeah, that sounds about right. And I don't think 8 cores is going to present any problems for the Kmap local page interface. So I think that's a good thing. So the question is, beyond this, what I've already spoken about, Kmap Atomic and Kmap being changed over to Kmap local page, how much more should the High-mem API change? Again, page address works. It's technically there. We're actually using it in some instances to get rid of Kmap calls where we know where the page comes from. I personally don't like this. I think that I think the fact that page address exists along with these other Kmap calls is confusing to people. And I'd kind of like to get to something where, there's a nice clean interface. But then the question becomes, if we're starting to I'll say force, but encourage driver writers kind of move to this new API, we need to kind of have a good justification for why they need to do this extra thing. Because if you're doing a Kmap, whether it's a mapping or really it's just adjusting the permissions on the direct map, which is what I started doing on this path, you're going to have an unmap or a reverse operation at the end when you're done using that mapping. And, some might see that as additional overhead. It's certainly additional code that has to be tracked. So, this is still kind of an open question. I think at this point, the API is definitely changing. We've deprecated Kmap and Kmap Atomic. And then the next thing that I want to mention is this API conversion is ongoing. I've got a tiny URL here, but at the end of my slides, I have the full URL. I created an Outreachy project. Some people may not be familiar with Outreachy, but Outreachy is an internship program to get people involved in kernel development. And I want to mention right now, actually, I'll just go on to my next slide. I think it's here. So I got an intern, Fabio Francesco, and he has been working very hard on converting as many Kmap and Kmap Atomic sites over to Kmap local page. I plan to try to pick up a little bit more of this work as well. His internship completed, and he's going to continue working on this, which is great. So we've brought a new person into the community, which is awesome, but we still have a long way to go. So with this, I'll actually back up here. If you want to visit this tiny URL and help work to continue this work, we still have we focus really on the Kmap side of things. Kmap Atomic, there's still hundreds of call sites across multiple subsystems that need to be converted. So I'm tracking who's doing what. This is another call out for people who would like to help. And part of what you can do if you're helping with that is looking and seeing how people are using this. So as an architecture micro conference here, a number of you are probably working on some of these smaller 32-bit boards. And maybe you can see how people are using this interface into that high memory by helping with some of these conversions. Anyway, that's my spiel for help. So,
Hey, Matthew Wilcox.
Go ahead.
Matthew Wilcox here. As I think I'm currently doing the page to Folio conversion, and so I've augmented the oh, there you go. I've jumped ahead and do you want me to shut up or shall I just say
no, please go ahead because you know more details about it.
Sure, no problem. So I've added one API which is which lets you map a single page out of a folio. So you get given 2 to the n pages in a single folio, and you can choose one of them to map, because that's kind of the API that we have right now. I thought this was going to be sufficient. Turns out I was wrong. When ext2 wants to handle a directory. It can a directory entry can cross a page boundary. And so for ease of programming, I mean, obviously we could handle that, right? We could choose to say, okay, we'll Kmap 2 pages out of a folio. But I think for ease of programming, really we want to just say, oh, I'm going to map the entire folio. And that seems to work fairly well for what you want this for, because you just need to say, okay, we will set the permissions on this entire folio to be accessible, and then we'll drop permissions at the end.
Right.
Now, I don't expect there to be a huge demand for supporting block sizes larger than 4 kilobytes and 32-bit systems with High-mem. Like on the same machine, I don't expect that to happen a lot. I mean, I think it needs to work, but I don't think it needs to be fast. And I would really appreciate it if somebody would tell me that I'm wrong. Okay, nobody's saying that I'm wrong. That's good. So
your case is just like one thing, the big like.
Just to clarify, your case is where you have one object that you're mapping, and it just happens to span 2 pages. So your maximum in like the XT case is just 2 pages instead of 1, right?
So that would actually work, but what's simpler from a programming point of view if we just mapped all the pages in the folio, no matter how large it is.
Okay.
And so my current proposal to do that, and I haven't quite finished writing the code for that yet, is that we just VMap it, which is going to be slow and crap, but we don't care because this is not a use case that comes up all that much. As I say, you have to have an ext4 file system with a block size larger than page size. So ext2, page size, block size larger than page size, and those don't. There's not a lot of those around. I mean, new ones are going to get created, I'm sure, but they're not common. And you have to be in a system that is 32-bit and has High-mem. This is not a large set of platforms, and I don't know if we care how efficient they are.
It seems like a case of doctor, it hurts when I do this.
Well, it does, but I want it to continue to work. I just don't think it needs to be fast.
Yeah. And you're thinking hide the VMap versus Kmap, like inside that folio interface?
Yeah.
Okay.
Yeah. So you just say folio map, and it will either do Kmap. It will do Kmap on Ira's system, and on some 4 gigabyte ARM32 system, it will call VMap. If it's larger than a single page. If it's a single page, we just use Kmap local.
Sounds beautiful.
Excellent.
Great. Well, thanks for being here, Matt. Oh, I'm getting an echo now. Anyway, thanks for being here. Yes, because I was going to bring up folios present a little additional complication. The other complication we've run into is some of these flush calls, and I put a bunch of stars here because these, and this is another kind of question to the group here, is these don't always get well documented. There's not a lot of documentation about when you call these particular. There's a flush decache range call in particular that we've put into a couple of the memory copy to and from page calls, because they seem to be needed on some architectures. Most architectures seem to just, they're a no-op. They get compiled out. But I did a little bit of research into this, and there's a whole suite of these flush calls. And there's not sort of a set of documentation of these are the ones that are defined that architectures can use. And then, so I don't, this is something I think that I'm kind of divorcing myself from. What our official stance is that Kmap isn't going to handle that for you, and it's up to the driver writer. So if hopefully if you're writing a driver that's specific for an architecture that really needs this, you call those. File systems are where things get a little complicated, because they're a subsystem that's designed to run on multiple architectures. So if people could speak up, or maybe somebody can do some documentation on these. Linus, there was a big thread in when I was creating some additional helpers for these mem copies, and Linus was saying, we don't need this. And then Arn, maybe you jumped into that thread. I can't remember if you were actually on that thread or not, but somebody jumped in and said, no, we still need those for some architectures. And, so documentation would be nice, because somebody like me who's kind of walking into this blind is, we're not always sure what to do with those calls. So that's just an additional complication.
Yeah, and I think, did you mention, Ira, that the real question here was whether any of these had interactions with preempt disable? Because I think that's what you were mostly worried about, right?
Yes.
Because now you're changing the preempt requirements of these Kmap operations. And so the question was, like, do any of these callers of any of these flush cache functions, of which there's like 800 variants, like you said, do any of them have any preempt requirements? Because if so, you might cause a problem there. So yeah, I think specifically, like, if there are preempt requirements of these things, that's what you want documented specifically. That'd be really cool.
Yeah, that's a good point. Yeah.
So I rather disagree that there's no documentation. There's plenty of documentation. In the documentation directory. Core API /cache tlb.rsc. The problem is that nobody reads it, and I mean, you couldn't find it for some reason, which I find bizarre.
What? Okay, well, let's. Could you put that in the chat?
I can't figure out which room we're using. I'll drop it into IRC. How about that?
That sounds good. And I'll go look for it. The other complication that we've had is testing for distros. I'm sorry, not for distros, but a lot of
we
distros
have
are
1-2 minutes left, so please try to wrap it up.
Okay, I think I'm pretty close to done here. So, okay, let me get into this. This is some of the ideas I have for the future. Number one, I think, is we don't want to support new High-mem for new architectures. So that's one of the big key takeaways I do want to get to. Oh, thank you for adding that cache TLB. So for all those coming in with new architectures, don't add High-mem support to your new architectures. If you have a 32-bit board you're developing and you want a lot of memory to it, why? Please help justify it. We've played around with different interfaces. Matt just talked about potentially using VMAP or something like that. I think that's what we really ought to go to, is making this work, but not necessarily be efficient. And thank you. I would like to thank all the people who have reviewed Conversion so far and helped us along with this. And again, I am making a call out to anybody who'd like to help.
Thanks, Ira.
All right. Thank you.
Should I use this microphone? I prefer. So using this one? Okay. Okay. Great. Is this good? Okay. Great. Assuming it works well. Great. Okay. Let's see if we can make it better. No? Hi, KB. Is this better? Great. Hi, everyone. My name is Ophir. I work for Google. Joined here today by my colleague, Junaid. My brave colleague, Junaid. It's now 2:30 a.m. In California. And today, I'd like to talk about a topic that nobody cares about, specifically security, more specifically, speculative execution attacks, and even more specifically, address space isolation. We first presented this topic in LPC and KVM forum about 2 years ago. We released an RFC. Since then, a lot of things have happened. There have been quite a few new variants of speculative execution attacks. What didn't happen is any interest or adoption of address space isolation, ASI, unfortunately. And I hope I can slightly change your mind today. So speculative execution attacks, like they started with Meltdown and Spectre, and this page is a bit out of date because I think there are a bunch of new icons that have joined. And those attacks kind of like typically give you a compilation error in your head when you try to understand them because they don't make any sense. What do you mean that user space can just access kernel memory? What do you mean that a virtual memory can access host physical memory? Because those attacks are microarchitectural attacks. Like we're used to think about what does the architecture give us? We can add and subtract numbers, we can multiply, we can divide, we can do branches. But underneath the hood, the processor is doing a bunch of crazy things. And I want to do like a quick survey here in the audience. Who thinks they understand well speculative execution attacks? See 1, 2 hands, 3, maybe 4, okay. Do you think you can write a proof of concept code? Okay, oh, that's also a few hands, nice. Yeah, so most people don't understand it. And I'm gonna do one more quick survey. With the new vulnerabilities, what do you think is the performance impact? If you use the new mitigations, like all the mitigations that we have, yes, KP. Oh. So he said, too late. Anyhow, like KP said about 30% if you use.
So if you do an indirect branch prediction barrier on security boundaries, and if that flushes the whole architecture state, it's really high. Like these are implemented in microarchitecture and take 2,000 to 10,000 CPU cycles, and the impact of not having the predictor units, like like having them stateless, is really high. So 30% on workloads, even higher for something that is very interrupt driven on VMs.
And yeah, as you said, it's pretty bad. And I can imagine it wasn't me, but I can imagine what happens when you go to your company leadership and say, hey, you remember this vulnerability disclosure we got? Don't worry, we got this, we have a mitigation. It's 30% performance impact. I believe you're not exactly the employee of the month when you do that. And the state of affairs right now is that the mitigations are quite unacceptable. And I think, at least publicly speaking, I don't think many companies are using like those severe mitigations that can reduce 40% of your performance impact. And the state of affairs today is that whenever you have a new variant, basically it's months of work, potentially in the order of 10 engineers or more. I have a colleague, which I won't mention his name, but he said, you know, I think if we had ASI, potentially I could get months of my life back. By the way, is there echo? Or does that sound okay? Okay, cool. And what I hope to advocate is that if we kind of like try to rethink ASI or think that maybe it's a good idea, then instead of months of work and instead of, I think I have some numbers here, for example, no, actually before that. Yeah, I think here the numbers I had here down below is that at least some public patch, for example, was 52 files changed, 1,600 lines changed. And I believe that with ASI, if we try to use ASI, every new vulnerability would be between 3 and 10 lines of code, probably a single engineer, maybe a bunch more testing to make sure it works, and probably not any new significant performance impact. So ASI does have performance impact on itself. It's between 2 and 14%, at least by our measurements. And ASI is also a performance, a mitigation technique that you can actually get better. So even if you have 10% performance degradation, if you invest a little bit more effort, to expand the allow list about what other spaces are allowed to be accessed, you actually get better and better performance as you invest more time in it. I want to show a little bit of graphs of at least some experiments I ran. This one is on Redis. So the blue line is the baseline. If you use the full mitigation, including stopping the sibling cores, the performance, at least on Redis, was about 87.5%, so that's 12.5. If we decide we don't want to halt the sibling core, then the performance degradation is a bit more than 2%. This is on Aerospike. If we stun the sibling core whenever we have an ASI exit, we get a little less than 7%. And yet another performance numbers, for example, for disk FIO, again, something like 1%, maybe 8%. And hence it seems very appealing, definitely compared to a performance impact of 30%. And I'm going to go a little bit into ASI details in a few more slides. And we understand that ASI is a bitter pill to swallow, specifically because it requires a significant modification to memory management. Specifically, we had to modify Kmalloc and vmalloc implementation. And we need to kind of like mark areas in memory about what is sensitive and what is not sensitive. Specifically in the implementation we released in the RFC, and what we tried now is basically assuming that all memory is sensitive and contains secret, except for stuff that we say are non-sensitive. So basically, we need to go to various Kmalloc and vmalloc sites and say, okay, this thing is not sensitive, this thing is not sensitive, this variable is not sensitive. And again, in a few slides, I'll get a little bit more into the technical details. I'm skipping them for now because we presented it in the past. But now let's kind of like jump a little bit into what are speculative attacks and how does ASI suggest to mitigate it. Any questions before we dive into those technical details? I think, yeah. No, great. So speculative attacks. So roughly speaking, there are quite a few papers about speculative attacks, and we can divide it into like 3 stages. The first phase is basically accessing a secret. It can be either by an architectural instructions or speculative instructions because of branch confusion. And the second step is trying to leak it, classically by trying to signal through the L1 cache, for example, what was the byte that we read. And the third step is the attacker actually figuring out what was the number that we actually read. Again, there's a bunch of papers about it. I personally have one that kind of like tries to dig into the details of how those attacks work. And basically what we're trying to do with ASI is to kind of like limit the exposure of secrets. So yes, you may access secrets, but we want them to not be leakable. We want to make sure the system in a very specific state when we can access secrets. And when we go out of that specific state, we want to scrub the secrets to make sure that a malicious VM cannot access them. And the general idea of ASI, which is not too surprising, is to use page fault as a way to distinguish between speculative access and non-speculative access. No speculative execution path can actually execute the page fault handler. Meaning, if a speculative access is trying to access memory that is not mapped, there's no mapping between the virtual and physical, the processor can't really give you the data. Like the processor has to walk the page table in order to understand what is the physical address and potentially bring it from cache or from memory. And this is what ASI uses. And the general idea is that we're gonna basically only map memory that we deem to be non-sensitive. And only when we need these other pieces of memory, only then we're gonna do a swap of the page table, and we map the entire other space. And the premise of ASI is basically that most of the time, even when we access kernel memory, we only access very specific kernel memory. So if we think about 2 guests or 2 VMs, and we have VM exits, typically guest A needs guest A stuff and guest B needs guest B stuff. There's also a little bit of other memory that maybe is common to many VMs, but is not too exciting, like the file descriptor table, potentially. And that's the general premise of what we're trying to do with ASI.
And let's see what actually happens, at least in our implementation for KVM. We want to do jump into a VM, and before we actually do the VM enter, we call ASI enter, which basically means we're going to flip the page table into a page table that only contains non-secrets and things that belong to this specific guest. And when we have a VM exit, before we can do any field execution, so first of all, technically we can just run, and if we don't touch any sensitive memory, nothing happened. We didn't pay any penalty. And if we have an interrupt that touched some sensitive memory, or we have a code path that touched some sensitive memory, then we're going to have an ASI exit. And the nice thing about using an allow list is that basically we don't need to think too long and hard about what are secrets. We just need to think a little bit about what are non-secrets. And we have a framework and a mechanism to discover what are those non-sensitive pages. And I'll go into that in a few more slides. But before that, a little bit of technical details. So for example, what happens on a page fault? So let's say we're trying to access some memory that is not in our mapped non-sensitive memory. Then we need to do an ASI exit. And before we do an ASI exit, we have the pre-ASI exit, which will stun the sibling core, meaning it's going to send an IPI and make sure that the sibling core is not executing anything to prevent a state in which you have still a VM running trying to steal information. And the second line here is actually an addition that I added for RedGrid, for example. Before we do the ASI exit, we're going to flush the branch predictors. And that's kind of nice. Instead of changing 52 files and 1,600 lines of code, adding the few lines of code that will just flush here the branch predictors, that's probably way easier than what we had to do for RedBleed. What happens on a re-entry to the guest? So we flush microarchitecture buffers that we think might leak secrets. And if we have new variants and we think we need to flash not just the L1 cache or the write buffer, then we can add a line here, basically that says, you know what, I need to flash one more microarchitectural buffer. And again, this addition is way simpler than the mitigations we had to do for new variants that have been discovered over the past 2 years. And finally, you basically tell the sibling core, okay, you can resume execution. Now only non-sensitive memory is in the microarchitecture buffers, and we're now only mapping the limited page table. And now the question, I guess the way more than $1 million question, is how do we discover these non-sensitive pages? So basically, the way we went about it is looking at a bunch of things. One of them is kind of like looking at the ASI exit versus VM exit. Basically, like a default mitigation that was, I think, proposed is just flush the UARC buffers on every VM exit. So ideally, we want this ratio of ASI exits to VM exits to be way less than 1. And when we have those ASI exits, when we have those page faults of accessing non-sensitive memory, there are 2 questions we want to ask. First of all, who's accessing the memory? And second of all, who allocated memory? And if we know who accessed the memory and who allocated it, then we can actually say something about, is this actually sensitive or non-sensitive? And here's an example of analysis we did on Redis. So maybe it's a bit hard to see, but these are ratios between ASI exits and VM exits. And on, yes. Yeah.
Quick question. This is when you're measuring ASI exits, you've already found some audited code paths, and you're taking a ratio of the ASI exit to that, or?
So yes, that's right. That's run after our pass of already marking. So when you start first, you have like 100% ASI exit to VM exit.
Got it. Yes.
Yes. And this is after like a pass we did, and this is on Redis. This is on, I believe, 16. Actually, we have 8 cores here, 8 CPUs. And the ratio here is between, depending on the specific CPU, between 1% and 25%, or yes, we have 50% here. And of course, we want to take this number way down. And this is how we evaluate how well our allow list is. Like basically, we want to take these numbers as low as possible. But at least we have a way to measure how much we need to pay in order to run SIT. Here's another analysis that we did on Redis. Basically, we wanted to see what code paths creates the most ASI exits. So this thing here is a CDF, cumulative distribution function. So this access was the most frequent one in the specific run, 276,000. And the lower we go, we have the code paths that created the less amount of ASI exits. And obviously, we want to deal with the big hitters first. Like you want to kind of like prioritize. Let's deal with the ones that makes the most ASI exits. And we also know, for example, okay, which code path accessed it. And then we can kind of like look at the code. Our framework kind of like tells you, okay, this is the code path that accessed this memory that caused an ASI exit. And this is what we believe. We have an estimation about what is the Kmalloc site or the vmalloc site that caused it. And with those two, you can actually say something about the memory. And also, you know that like, okay, I may need to add here this annotation of GFP non-sensitive because I think that this memory that's being accessed, if a malicious VM will try to read it, I don't think that presents a threat either to other VMs on the machine or us, the host, Google. And yeah, go ahead. Yeah.
VMs in here. Where is the user space attacking the kernel side of this? Is that also somewhere, or is that just not
the user space stack? The user space stack, not the kernel.
I'm saying so you're talking about VMs leaking data to each other.
Yeah.
Is the main case here?
VM, at least in my mind, a malicious VM wanting to steal data either from the host or from other VMs. Yeah.
So what about user space and the kernel's interaction here, where user space is trying to attack the kernel and get data out of the kernel?
So from a VM or not, regardless of VM?
Just bare metal.
So we believe we can extend ASI to also replace KPTI. We have not done it yet.
Dave, it's more complicated. A short answer.
Yeah.
ASI is pretty much about how KVM does exit and what mapping is changing. If you do it for more generic use case, it's kind of revamp entirely how kernel handles kernel page tables.
Okay.
Yeah, Junaid, I think Junaid is online. Do you want to say something about replacing KPTI? If you can, do I need to do something to let Junaid speak, or
is it?
If it doesn't work right away, we can also just read it.
Yeah, that's fine. Yeah, okay.
Can you hear me now?
Yes,
yes.
we can hear.
Yeah.
Yeah. So I mean, as Phil mentioned, so we do think that we can extend it to user space as well, using the same principle. Basically, like we can map memory that's accessed using most system calls. It's one thing that's kind of not yet clear completely is how much memory we'll need to map. So with user space processes, I mean, there's a lot more system calls than there's like types of VM exits. So we will probably need to map a lot more memory, and which means that we might need to do some sort of automation to actually do the analysis that we just mentioned. Because doing that analysis manually is going to be much more time consuming. So that's something we're still looking into. And another thing we are also actually looking into is if we can also like possibly like switch to a deny list approach instead of an allow list approach. Basically, like everything is non-sensitive by default except for explicitly marked secrets. And that would be much easier to do for, let's say, user space processes, because then we don't have to analyze a whole lot of different code paths.
Yeah. Do you have an idea of the scope of, I mean, how many lines of code are we talking here that have to be modified to do VMs versus user space, for instance? Like, are we talking hundreds or thousands or tens of thousands?
No, I don't think it would be that many. So like in terms of the infrastructure itself, I think it's probably going to be like a small number of hundreds. Like in terms of more, and like just in terms of the memory annotations, it can be much more. But again, so memory annotations are like if you, for example, switch to a deny list space approach, then even there isn't even going to be a difference in the memory annotations either.
And is this just KPTI? I mean, there were lots of ways to leak stuff out of the kernel from user space from some of these attacks. So is this just KPTI, or is this everything?
We could do, certainly we could do things beyond KPTI as well. So it basically like depends on what you do in your ASI entry and exit handlers, right? So if there are like any other mitigations which we can avoid by simply flushing some particular microartificial buffer, or flushing some branch predictor or whatever, we can add those in the ASI entry and exit handlers, and then we can remove those existing mitigations.
I also think that for Cisco entry exit to doing ASI entry exit will be way more expensive than doing this for VM entry exit.
It's probably yes, but again, it depends
From
on
what I tried, it was like 10 times more expensive. But
right. But it depends on what you have mapped, right? So you don't need to do on every single syscall, right? You only need to do it when your syscall touches something which is not mapped in your restricted address space. And if you and that's certainly a challenge, like, because we will need to map a lot more in order to look at reasonable performance for syscalls. And that's certainly a challenge. So, but if we, assuming that we do map all the things that are commonly touched by the various syscalls, then at least in theory, it should be able to get reasonable performance, right?
well, it depends on how you divide sensitive versus non-sensitive.
Yes. Right.
If you have a lot of sensitive, then performance will go down. If you have most of memory unsensitive, then there is no performance hit, right?
Right. Yeah.
So I think like the other question is, have you tried comparing the other approach of the denialist? Like, have you tried doing the ASI to VM exit ratio of 0 to 100?
So I think Junaid is trying to kind of like implement the denialist approach, if I'm not mistaken, but we haven't have anything that's working now. Is that right?
Yeah. It's I'm still working on it, but we haven't really tried it yet.
And do you have examples of code paths that you consider as sensitive, and the ones you don't consider as sensitive, just for the audience here?
So if you kind of like, first of all, in most VM exits, nothing is actually interestingly happening. Basically, you had like a timing interrupt that didn't do anything interesting. Maybe you access some file descriptors, but you didn't actually access data or files. Then most of them are non-sensitive. If you're sending something to a network, potentially to another VM under your control, then also it's non-sensitive. Most of the timer ticks that creates a VM exit basically are non-sensitive. We have like an example, I believe we did publish in the RFC our list of non-sensitive, right? But most of it is file descriptor tables, something about networking, at least between VMs. Most timing interrupts don't really require you to have an ASI exit.
Okay. I was wondering, like, if you're writing to an MSR, for example, from the VM exit, if you're intercepting an MSR, right, that would be potentially where you need to be extra careful, right?
Yeah, but in MSR, I'm kind of like half guessing now. I don't think that's would that be a sensitive write to an MSR?
That's user controlled input even after you flush the GPRs.
Yeah.
Like you can control input, and if you find a gadget that can load a register from your MSR, and then you can have that input being used in another gadget in a follow-up, then you have an info leak.
That suggests, I guess, that MSRs contain sensitive information.
No, it contains user controlled input. So yeah, if you have your sensitive information always unmapped, then. But my question is, how do I find where the sensitive information exists? Right. This is.
So you're talking about the deny list approach, not the allow list approach.
Whichever. Like, how do I find the location?
So with allow list approach, it's kind of like, I guess, it feels a bit more comfortable because every memory that you add, you've seen what it is and who allocated it and who accessed it. And that way you don't need to say, hey, maybe, I don't care where the secret data is because everything is a secret except for what I just specifically said is not a secret. If you're trying to go the next,
Sorry, you're also considering different threat model. The ASI mostly, as far as I understand, works against the infiltration from data from other guest or host. And you are talking about a threat model where there is one VM can control the execution of another VM.
No, I'm talking about the guest to host thing itself.
But it's not infiltration; it's rather control. It's not stealing information, but modifying the behavior.
It's an info leak. So what I'm saying is, I do an MSR, right? I intentionally write something to the MSR that I want to be in, let's say, R1 register at some point, right? Then I do a branch target injection, right, at the MSR, right, and I take this and use this MSR load to load R1, then use another gadget that I can, where R1 is used for like an mmap syscall or something, and then I have an info leak there. So it is speculative.
But the data has to come from memory, I assume.
Yes. that is where the sensitive and unsensitive
Yeah.
mapping.
So at least I believe, unless I'm mistaken, is since if we're taking the allow list approach, everything will be unmapped. And once, okay, you can control the gadgets, you can control the speculation path to do whatever you want. But once you actually want to access the data, the processor will not have the mapping of virtual to physical, and it won't be in L1 cache either. Yeah. So I think, I mean, we basically done at least with slides, and at least we're trying to advocate that maybe we should reconsider swallowing the bitter pill called ASI, even though it's kind of like a non-trivial mechanism.
I missed this, and I'm not that active in this area, so forgive me for my probably stupid questions. But what was the original reason for rejecting this? Performance or?
So I don't know if it was rejected, but there seemed to be not a lot of interest. Jonay, do you want to comment about that?
Yeah, I don't think I mean, we haven't like seen anybody explicitly saying that we don't want this. It's like yeah, it's just as Sophie said. So there hasn't been there doesn't seem to be like any interest as such.
Almost here?
No.
So I'm one of the x86 maintainers. I looked at this. So, I mean, the reason that I didn't like it, and it isn't merged now, is because it's a lot of code. It's a lot of future commitment to this stuff. And there isn't really broad use for it. Like you said, this doesn't even like consider the syscall path, which we kind of care about. So, I mean, look, it looked really, really interesting up front until I started to see the details and how much code this has to change and how much of a permanent maintenance burden in every little corner of the kernel this is going to induce.
No, also, we have separate syscall entry paths now, right? We have the regular system calls, but we also have IO uring.
Not even considering that one.
Which is a whole separate thing.
Yeah, true.
And I think we're running out of time, so thank you very much, Ophir.
Thank you.
You can keep it. The next is me. Can you hear me? The next, probably I should get rid of this. It's not as exciting as security and data spaces and 40 patches or so RFC, but while working on Memblock, bootmem, everything, I've noticed that we have a really nice representation of the memory with struct page, struct folio, memory descriptor, whatever it is for the runtime and the core memory management to work on. And then we have several coarse grain memory representations like Memblock, the driver CSFS interface, E820 that lives for entire system life. There are also things that PowerPC do, and so on and so on. And we also have the resource tree and system RAM under IO memory sources, which is kind of awkward to my view. But so maybe I'm just overreacting, but I think they all should be at least consistent. And probably we don't need as many of them as we do have now. So, oops. The original idea of the project was to create a single representation for everything there is representing the physical memory in large chunks like start and flags. So I'll start with how what's going on today around this area. We start with firmware that detects the actual physical memory in some way, either it's in a non-volatile storage, or the firmware may run some memory test to identify what DIMMs are actually installed in the system. The firmware uses some of the memory for its own needs. for x86, for instance, there are CPI tables, CFI services that remain live during the system lifetime. And then the firmware creates some memory map for the next levels. It can be bootloader, kernel, any of them. Each architecture uses its own unique way to pass the memory map to the kernel. And there is also sometimes additional way to pass NUMA topology and the node division to the Linux. For instance, x86 uses E820 to create the initial memory map, but the E820 doesn't include NUMA information that's read after some time, eventually from the ACPI tables. During early boot, kernel actually doesn't know what its physical memory is until some point at setup arch. So for the most time, setup arch passes the physical memory map created by the firmware. At the same time, usually architecture creates its own view of how the memory is seen. I think it's true for everybody except RISC-V and ARMS. And then the memory ranges from the architecture specific representations are passed to memblock, and then memblock feeds them to the generic memory management. Somewhat in parallel, there is also setup of the NUMA topology and the assignment of memory ranges to NUMA nodes. And again, there could be parts of this information in memblock in the end, and parts of this information live in additional structures. For several architectures, there is NUMA something and NUMA something else. And then this is the most amusing piece. We have the system RAM IO memory resource that that is initialized on every architecture that supports kexec. Not every architecture actually has system RAM in the IOMEM, in proc IOMEM. So there are some hard-coded places where we had RAM areas to the kernel, to the proc IOMEM essentially, and they also reserve kernel code data. Again, it depends on architecture. The format is not really consistent. The diagram here is from x86. On RISC-V, I think the kexec folks went wild and they reserve like everything. Wait, Palmer.
Yeah, I think it's actually just broken. Like we've got some patches on the list. I think there's not having our own internal representation, I think, has led to some sort of cyclic dependency between the various memory allocators being set up, and we're just pushing bugs around in a circle, basically.
Take a look.
Yeah. Okay.
Yeah. So, and then I think a core init call or driver init call, there is setup of the memory sysfs for architectures that support memory hot plug. And although most of the time Linux memory management or Linux in general doesn't rely on these coarse-grained representations, we still have some places that need it. For instance, x86 makes E820 mapped any exported symbol, and it can be used by any module actually. There is a function that converts physical address to the desired node for NVDIM plugin, for NVDIM hot plug. A PowerPC keeps they call dynamically reconfigurable memory information, and this represents their view of the hot pluggable memory. S390 is
has a weird way of keeping track of what memory was there originally and what memory can be passed to the second kernel with kexec. There is also a nice function that walks the resource tree to understand if page is in RAM. And there is walk system RAM range to do something for every piece of system RAM memory, because quite frequently it's not contiguous. And both ARM and ARM64 rely on memblock and runtime to determine whether the page is in RAM. I think it's mostly on IRMF pass, but there could be other places as well. Maybe some folks from ARM would give more details. And there is also kexec that needs the information about system RAM layout. Currently, for the most part, it comes there from proc IOMM. Kexec parses proc IOMM, finds system RAM areas, finds reserved areas, makes sure that kexec is loaded at the holes between the old kernel and the second. It tries not to fill the places where the first kernel lives. There is something that x86 only can use that lives in sys firmware memory, like a comment in kexec says, we have an architecture-independent way of parsing it, but essentially on x86, because it directly exposes EH120 structure to the sysfs.
Why is it called IOMM?
It's originally there was IO memory resource that listed all PCI bars and other IO memory resources. And when kexec implementation came, they needed something to expose physical memory layout to user space. So they've added system RAM under the IOMM. Billy wants a mic.
No, I think it actually predates, having system RAM actually predates that, because we used to we used to do PCI bar resizing ourselves. Well, I guess sometimes we still do on some architectures. And so you have to know where everything in physical memory is, which includes RAM, so that you don't put a PCI bar over top of your RAM.
But we didn't expose it to the user space before that, I think.
Oh, no, we did. We did. Yeah.
We did?
Yeah. Because if it's in IOMM, it gets.
Maybe my archaeology wasn't right. So.
Yeah, I mean, you know, I'm thinking about how things were 20 years ago. I mean, you know, it's
2 years or so I did some archaeology. I think system RAM appeared in proc IOMM, not under the IOMM resources, but in proc IOMM.
Well, they're the same thing. Proc IOMM is always just exposed the IOMM resource tree.
I think it came in with kexec, but
no,
I might be wrong.
that. Well, I think maybe in x86 it came in with kexec, but I know we had it.
Itanium.
No, I know we had it before that on PRS. Anyway, it was, yeah, it's a long time ago.
Yeah, so these are the issues I see. Maybe I'm overreacting again, and we just can't live with it. But what was I was thinking that we need some generic representation for generic coarse grain representation for the physical memory that will be consistent with what firmware gives us, and that we'll be able to keep proc IOMM at least for several years as it is now, and that it will be flexible enough to accommodate architecture-specific needs, like ARM has the no map areas, x86 has a lot of additional information about how exactly reserved area should be named, ACPI something or EFI something. Palmer, maybe you too have something to add there, I don't know.
Sure we will.
And there are several alternatives to do that. One is to create yet another new data structure, probably based on Xarray. Kidding.
Maple trade.
No, we'll stick to something simpler. And there is a resource tree that can be extended probably, or just use it, but then we are stuck with proc IOMM like forever. And there is memblock that already does this for ARM. It kind of does this for RISC-V until I've heard about recent problems Palmer mentioned just a few minutes ago. But the problem with Memblock is that for x86, the integration between E820 and Memblock really sucks. And there's really a lot of things to do there. So I need volunteers. Anyway, yes. Can we...
I volunteer to talk to you about it. I'm not sure how much I'm volunteering to do about it, but
there is, so the Coreboot and Linux boot communities are working with Intel and whoever else wants to jump in on, because Intel has this humbly named universal firmware project, but I think we've sort of convinced them anyway that FDT would be better than what they've got planned. So
wow.
So if you're all comfortable with FDT, I think that we may be able to drag it into the x86 community, and if that'll work, that'll work. So
I'm afraid it will take like 10 years or so.
That's okay. I don't plan to be doing this in 10 years, so it's cool.
Right? Right. Today, ARM and the PowerPC use FDT. Some of ARMs and the PowerPC use FDT to communicate the memory between the firmware and the kernel, and then it's parsed into Memblock.
Yeah.
And then it leaves, instead of doing the OF node search and so on, we have everything in Memblock, where it's a bit nicer data structure to work with.
Right.
So I'm okay with FDT, and there are questions over there, so throw hard.
I can't throw it that far.
And they're pretty sturdy.
Yeah, I was just going to say, just using FTC doesn't really solve the problem. So on ARM64, for example, if we're booted with EFI, we need to use the EFI memory map. It is not possible with the current DT memory nodes and all that sort of thing to represent the same thing. So we, on ARM64, depending on how we're booted, we either use the EFI memory map in the kernel or just the DT memory nodes. The whole point of putting it into Memblock is that we have that consistent representation from that point onwards. But just using DT doesn't really solve the problem.
So for me, the obvious thing, I work on Memblock, so for me, the obvious thing is to use Memblock for that. And then for architectures that need the coarse-grained representation in runtime, for instance, memory hot plug and so on, it just enable keep Memblock for everyone, probably for every NUMA-capable architecture. Create some way of generating the resource tree system RAM apart from the existing Memblock. It can be done pretty late because it's anyway that it doesn't get used until a driver driver init calls. And then there is, as I said, a huge gap between E820 to Memblock that somebody needs to be filled. And the idea I was toying with for some time now to rename Memblock alloc back to bootmem alloc. After seeing tons of patches for rename page to Folio, I think I'll send it. Yeah, so that's pretty much all I have to say. Now I'd like to hear what others have to say.
One thing you didn't touch on here is memory hot plug.
Memory hot plug has its own mysterious ways.
Yeah, but should it? I mean, if you're using Memblock as a physical memory representation, I think Memblock needs to be used for hot plug.
It is used already.
Oh, okay.
Because of PowerPC and ARM64.
But on Intel?
Well, it goes from a CPI to memhp, right? And then memory hot plug .c calls add memory. Then it calls Memblock add.
Oh.
Or maybe the other way around. I don't remember exactly, right? But and then it actually lets you use the memory. And depending on the flags they create, memory map or make the memory online. But I don't think is David here? No.
he knows for sure. But there is memblock add after or along with add pages. So the information about the hot plug anyway gets from the CPI. So there is something that should parse it. x86 also does E820 add because the table should be up to date because kexec needs it. So any more questions, or we just have 10 minutes for early break? Mark, do you want to come over here and...
I'll just hold on to this mic. I was just going to say, you mentioned kexec on x86. You have to update the E820.
I don't know, I don't really hear you.
Sorry. You mentioned that on x86 you update the E820 memory map because the next kernel might need it when you do a kexec. ARM64 takes a very different approach there, where we try and keep all the firmware provided data structures pristine and unchanged, and we expect the new kernel to go and reinterpret those as is. So there's some different requirements across architectures there. That's all I wanted to point out. We do that because it means that if we have a bug in the first kernel where we manipulate things, we don't inherit that into the next kernel. We just can do the right thing and don't have to bodge around our bugs for it.
Mark, do you keep the DT that you pass to the second kernel, or
we
you
keep
reconstruct it from memblock back?
We keep every firmware provided data structure. So the original DT we still have. For kexec, depending on whether you do kexec file load or a user space kexec, where you do purgatory, for the kexec file load, we just pass the original DT on, or a copy of it that's slightly modified with the command line, but that's basically the only modification we make. If you do a user space kexec, you provide your own DT, but we expose the original DT in sysfs so you can get hold of that and do whatever you want there.
But kexec still reads proc IOM to get the areas.
It reads proc IOM to figure out where it can place
Where to put
things.
the segments. But it doesn't use proc IOM to recreate the memory map for the second kernel. Unlike x86, that kexec also uses proc IOM or sys firmware memory to get the new E820 for the next kernel.
Are you sure about that? Because at least in the last few years, on startup, it saves copies of E820 map, and at least when in my use, it's using the original one at boot time when it does a kexec. At least in the stuff we're doing, that's what I see.
I'm not sure about the EFI only systems.
Yeah, I'm thinking of the EFI systems because that's all I've got.
EFI only systems, kexec reads the sys firmware.
But you mean user tool or the kernel? Because in the kernel, what I've seen is
anyway E820 even though in EFI only systems internally.
Yeah.
And I think it gets there from for the second kernel as well.
We can look later.
I'm not sure.
I'm pretty sure that's
not really
no longer true.
With kexec details, but
yeah, I think nowadays, if you look, it didn't only came in the last couple of years, but they actually scarf away 2 copies. I don't remember why, but there is 1 copy they restore before the kexec because we depend on that at Google. It's load bearing now.
Okay.
And that has to work or we're screwed. But that's what we've seen.
When I took a look at kexec just recently, they built the new E820 map, even on the EFI only architectures, I think, but I might be wrong
here. Yeah. Okay.
There is one question in the chat. I don't know if it's already been answered. Punit asks, but then how does the kexec kernel find the hot plug memory?
So to give context, this was to Mark's.
When the kexec runs, when you load new kernel, there is you hope there is no hot plug event. Like I don't know the details about what happens if there is, but at the point where the new kernel starts, there is some set of memory that exists there. It's up to date with the E800 or whatever kexec uses is up to date with what memory is there. And when the new kernel starts, it gets a table, and then if memory hot plug happens afterwards, the second kernel will notice.
Yes, Arnd.
Yeah, so on PowerPC the approach was always like one of the original uses of having the flattened device tree in the first place was that you can have hot plug devices, which could be memory or anything else really, and have it after kexec. So with the ARM approach of having the pristine FTT, that obviously does not work. So the PowerPC device tree is kept in memory. It can get modified if another device gets added, and then after kexec, you actually have a new FTT assembled from whatever the first kernel had, which is a very different approach of what we have on ARM.
Yeah, I was just going to say, Mark, again, on ARM64, we don't support hot plug of memory while using DT, but if we booted with EFI and we have ACPI tables, we can use the standard mechanisms for that. And then when the new kernel comes online, it goes and just rediscovers the hot plug memory for the existing standard mechanisms there. So we can support that. It works. Our only requirement is that if memory exists at boot time in the EFI memory map or the FTT memory map, that cannot be removed.
Your multiplicity of firmware is astonishing. Yeah. Didn't we have anything else? Let me check chat. I think we're running early, and we will be first for the line and for snacks.
There is nothing in the chat. I checked.
Okay, perfect. So if there are no more questions, then thank you, everybody. And we are starting back at, I don't remember how long our break is, till 12 Dublin time. Half an hour break. So see you in half an hour, guys. Right. Do remote people hear us? Say something on chat, probably. I'll try to find the chat.
Okay. Can I speak?
Okay. So if anybody wants to ask a question from remote, please turn on your camera so we'll see you. And the next talk about the new child in town, the latest architecture that got merged into the kernel LoongArch. Please. Peru.
Okay, hello everyone. I'm Chen Huacai from China. Since my colleague Liu Jieming and me are attending virtually, and our oral English is very terrible. So this session will be represented by our partner, Wang Xuerui. Thank you.
Oh, and can you hear me? Oh, okay. So for this talk is LoongArch, what we'll do next. And I think I'll first begin with who we are. Okay, so I'm this guy. I'm this second guy. And the person just speaking is Chen Huacai, which is the LoongArch maintainer. And me, I'm a Gen2 developer, LoongArch reviewer, among countless other roles in the community. And I do all of this as a hobby, so I'm very proud to be the hobbyist hanging around here. Yeah. Okay, so let's get. So what is LoongArch? So according to the introductory commit, it's a new risk ISA, a bit like MIPS or RISC-V. Yeah, it indeed is. It's basically very similar to RISC-V, and when you look at its userland programs, but its privileged architecture has a lot of the reminiscences of MIPS. And here are some numbers. There are 3 ISA subsets, the LA32 reduced, standard, and LA64. There are 4 privilege levels, much like the 4 rings of x86. Yeah. And like many common RISC architectures, there are 32 GPRs, 32 FPR or vector registers, and 8 floating point condition code registers like MIPS. There are many models currently available or is planned to come on the market, including the 3A5000, 3C5000, 3C5000L, 2K1000LA, 2K0500, etc. I think next year they will have the 3A6000 available, which is a talk upgrade with microarchitecture updates, and that will be more performant. For further information, you could check out the official docs or check out my unofficial FAQ. Yeah, you can actually download the slides and click on those. Yeah, so I'm not reproducing the links here. And by the way, I think maybe some of my fellow Chinese friends are watching online. You could go to the LPC presentation detail page and download a Chinese language version of this slide. Yeah. So what we have done. First of all, I'll give you an overview of upstream status of LoongArch and the current status of upstream kernel. Okay, so as of today, essential support is mostly upstreamed. Binutils, GCC, Linux, glibc, Go, libffi, libonline, systemd, etc. These are all done. Many are already released in a tagged version, and some are still awaiting, but it shouldn't be far. And some of the most prominent missing pieces like LLVM, Rust, and Muscle are porting is already on the way, and patches have already emerged. For LabSecComp, I think the patches already done and just waiting for the official stamp. Yeah, and its ELF PS API just got revised slightly incompatibly. More on this later. And the overall API is stable. And multiple distros are already available. We have Gen 2, Arch Linux, and 2 efforts of Arch Linux, actually, and Slackware and the CLFS book and the reference CLFS build for it. Yeah. Actually, I should be presenting on this LoongArch laptop right now. Yeah, this is one of the LoongArch laptop. It's an engineering sample that I got. Yeah, and it's running Gen 2 and XFCE. Yeah, and we have ported LibreOffice to it. So in theory, we'd be able to present on this machine, but the keyboard is having some problems, so I couldn't unlock it. Anyway, yeah, if I was able to present you its interface, it'll be just LibreOffice opening this slide. Yeah. So, so what's the status of the upstream kernel? In its current shape, it supports UEFI plus ACPI systems, and we've managed to push the Arch support and stabilize the UAPI into v5.19. And sorry for the rush. If some of you, some of the reviewers are there, yeah. Sorry about that. And for this custom merge window, we have ready IRQ chip, PCI, and provisional ACPI definitions. Also, some minor additions like VDS or get CPU and something else. But for the next merge window, we should have most things ready, and this version's gonna mostly work out of the box. We have the ACPI 6.5 finally released, so we switched to the final definitions, and proper EFI boot support, and eBPF JIT, queued spin lock support, and perf events. And there are more to come. There are still some features in the works, such as proper suspend and resume support, and sound support for the LS7A chipset, and many more. Okay, so yeah, sure.
Microphone? Yeah. So I'm a maintainer of restartable sequences, the RSEC system call. So the get CPU VDSO becomes not really useful once you get a glibc 2.35, which enables restartable sequence, and use the current CPU ID field that it's a load, right? So there's get CPU is just loading that value from user space. So and they use that on ARM64 because they don't even have the get CPU VDSO. So so based on this, I mean, that may not be used much. The other point there related to restartable sequence system call. So I noticed that LoongArch has have RSEC defined in the kconfig. However, the self-test, the kernel self-test code that needs to be specialized for this architecture has never been provided. So there's no testing of that system call on the architecture. So I was wondering, do you have a timeline to provide this test code? Because this is kind of assembly that is LoongArch specific, and I don't have any knowledge of that assembly, right? So I would recommend either pushing a patch that removes the AVRSEC support from LoongArch, or having a short timeline to provide this testing.
I think I've just seen commit adding LoongArch into the k-self-test mechanism recently in one of the development branches of Longsang's fork. So this construction may well already be in progress.
Very well. Thank you.
Okay, next. So we'll get quickly to what we'll do next. And yeah, we have the old world problem, and we are gonna talk about support for alternative boot protocols, the way forward. And we originally planned to talk about the way forward for generic EFI boot flow, because this question popped up when we were trying to push the EFI stub support for LoongArch upstream. But in the coming 1 month or so, RB already finished all of this. And the code is bound to appear in version 6.1. Yeah, so this is all sorted out, and we won't cover it today. And kudos to RB. Yeah. Okay, so let's begin with the old world problem. Basically, we'll start with the background and talk about the various incompatibilities all over there. And finally, we will try to provide ways forward. Yeah, not all of them is feasible or even sane to implement. So that's why I'm bringing those approaches here for discussion. Yeah, so this is the fact. Earliest LoongArch ports were basically copy-paste of MIPS code with mass replace strings. So we even have little gems like Bogo LoongArch and LBT LoongArch for that. LBT LoongArch means Longsang binary translation. So they appear to be able to translate from LoongArch to LoongArch when they basically, they obviously meant MIPS here. Yeah, and that typo was quickly fixed. Yeah, so this is all rushed for apparently non-technical reasons. And they have to switch away from MIPS in a relatively short time frame, and they were forced to just quickly put something out so products could come to the market quicker. Maybe I'm not a Longsang employee, so I might not be in a position to comment on this, but this is the fact. And obviously, this is not gonna fly. So after meeting some stern faces and objection from the community, they eventually they switched to the new API, which is largely modeled after that of the RISC-V. Between the two APIs, the ELFPS API and calling convention are mostly unaffected, fortunately, but other parts not so much. And there are differences and incompatibilities at every layer, which I will detail below. Yeah. So starting with the PS API, we have different relocation types at first. So in the old world, as we call it, they use stack machine relocs. Yeah, the relocations are calculated with the stack machine model. By looking at the Binotil sources, it seems only RL78 and RX architectures are using this style of relocs, and I don't think it was a coincidence because both of these two arches come from Renaissance, but apparently this is not gonna be sustainable in the long term, because stack machine, the computation like this. How do I zoom out? Okay, not like so. Oh, this one. Zoom in, zoom in, zoom in, zoom It's like this for one single, this PC at U12I is like AUI PC. It's exactly like RISC-V's AUI PC, by the way. To calculate one relocation, we need this much relocation records. It's push, add, push, push, add, push, shift right, push, shift left, sub, push, shift left, push, shift right, and then I finally pop into the instruction slot. So this is quite insane, huh? Yeah. And this is absolutely not gonna fly because the modern linkers like LLL VMs, LLD, and mode, they cannot accept such a serialized processing because in processing those relocations, you obviously cannot have any parallelism. And this is not gonna be architecturally accommodated by the linker projects. So they have finally switched to a more classical style relocations like this. Here you can see it's more rational. Yeah. So this part is gonna require some modifications to various downstream projects, like the Linux kernel because it needs to load modules, and the grub tool because it has some modules too, and LPC support, of course. Yeah. And we also have marker in the released bit domain of eFlex field. And so with the very recent New World toolchains, I don't even know whether the patch has even been posted. So it's supposed to be 0.1 for very recent objects and 0 for old world objects. So yeah. And this is about the PS API. And then there's the firmware level incompatibilities. The old world UEFI has all its pointers in virtual addresses, while the new world has physical addresses as with everyone else. It might be the case that the original scheme was devised because the kernel expects the same direct mapping window config as the firmware already set up. So it might save literally 3 to 6 instructions.
So in the EFI spec, it's for all architectures mandated that the PA equals a VA, right? So there's always a one-to-one mapping. So why would they even be different?
Actually, it's direct mapping means you look at the VA's prefix, and if the prefix matches the DMW config, then the rest of the VA gets interpreted as the appropriately offsetted PA. So in a way, it is the PA, but it needs the prefix. So. And I believe the kernel is still using DMW config today because this way, I think access to user memory might be more performant. But doing so precludes the possibility of supporting memfd secret. So they are trying to, I believe they are working on replacing this DMW kernel scheme with the proper TLB mapped kernel. I believe they were working on this, but it will require some more work. So not in the immediate future. Okay. And the ACPI tables shipped systems with the old firmware have different incompatible layouts of their ACPI tables. Yeah, so some end users may remember having to carry an ACPI table patch in their init-rd enable in order to be able to boot. And finally, for the boot protocol, for the old world, they simply carried their boot protocol back in the MIPS days forward to LoongArch. So it's the struct boot params interface, or BPI for short. It's for OW, old world and early iterations of new world kernel. So this is all translated via a special grub tool. Yeah. So from this illustration, you can see the new world boot flow is a lot more normal. Yeah. And you really don't want to go this way, which is why it got shut down in the first place. Okay. Then there's the UAPI difference. So I may need to go a bit quicker. The number of signals is this doubled in the old world, which is the same as MIPS. Well, it's the same as everyone else. And we have deprecated some of the older syscalls with the modern variants. And we have slight differences for ptrace and SIG context. So LPC and the various low-level pieces need to be adapted as well. And we have this different LPC symbol version and LDSO path. Yeah. So how do we unite the two worlds if we want to do it? The goal is obviously digital preservation, possibly by allowing OW binaries on new world kernel. So the first question is, do we even want to go this way? Because first of all, old world is bound to go away, and a full old world system could be emulated with a full system emulation, or with the one-like approach where everything's nicely isolated. We might not want hybrid sysroots after all. And we might want to run new world kernel on either flavors of firmware. So we might have to push BPI support upstream if we decide to go to support this. And for this, I think we do care for those early systems to get updated firmware. We do care for those systems who are not getting those updated firmware, so users aren't left unattended. Okay, so basically, I plan to go through this real quick because actually in the recent days when I was busy polishing these slides, I think it might not be a good idea to even try supporting the hybrid sysroot case. So we might be able to divide by the syscall boundary or by some internal mechanism, like trying to tell if process is speaking OW by looking at its first sigproc mask call to see what number of signals it expects. I don't think that this is gonna be upstreamable. Yeah. So and then we have to handle cross-world execs. So this is becoming really tricky. So I think I'll just ignore this slide. Yeah. Anyway, it's all in the PPT, and we could all continue the discussion on mailing lists. Yeah. And finally, for alternative boot protocols, why are the boot protocols matter? First, for BPI compatibility with those early hardware, and for enabling resource-constrained use cases to boot via DT to allow vanilla Linux on those small devices. Finally, there's, of course, the flawless firmware, like core boot. So we get to provide users more choices, which is always better. Yeah. For BPI compatibility, we might be able to design some clean shim, like these three approaches that I have illustrated. BPI is basically a decorated indirect UEFI boot with the UEFI table and ACPI table in some different location than standard UEFI and New World boot flow. And the memory map, yeah, memory map is differently shaped. So we could shim at the inside the kernel, or we could make a special grub tool, or make our own UEFI shim that translates old world UEFI to new world UEFI. Okay, yeah, maybe the path of least resistance might be the third approach. Yeah. So I'm still just showing the various possibilities, but I think we might eventually go this route. Yeah. And finally, there's the DT boot question. This is likely doable without much friction because DT is already some accepted standard, only that it lacks standardization for this architecture. But today I don't have much information to share because both Longsong presenters are not working on DT kernels as far as I know. So to the Longsong people working on this, who might be watching this watching this presentation, I need to say to you, communicate, communicate, and communicate. Yeah, important things get to said thrice. Yeah. Finally, acknowledgements to my employer and Longsong and all the community power who's been supporting us. Yeah, including Gen2 developers Stillfridge and Sam, and FlyGoat, Hoge Langley Forces, Kirigami, and Revi, Xiruo Yao, and others in the Telegram Longsong user group. And of course, countless others that I might have forgotten to mention. Yeah, and that's all. Thanks.
Yeah. So I'm a maintainer of the user space or CU library. There's been a Longsoon support patch sent to me maybe a year ago. I asked back a question about the architecture. I read the architecture manual. There does not appear to be any byte-wise and 2-byte atomic instructions that I could find in the manual. However, the patch enabled support in my library for those instructions, and those are tested, and somehow the test might have passed on someone's system. So I asked, are there such? So I replied to the patch author, and never got a clarification on whether Longsoon has 1 and 2-byte atomic instructions. And second, I mean, has there been tests done, or can I receive a board to do my testing in my own test rack? So those are my questions.
Oh. Okay, so actually your first question, whether LoongArch has 1 and 2 bytes atomics, subword atomics, the answer is no, but there might be a way forward because actually I think for the next presentation by Guoren, he's gonna present the LLSC architecture emulating the subword atomics with forward progress guarantee. Actually, if the microarchitecture assists, have some assistance, this is actually doable, even with LLSC emulation of subword atomics. Also,
but in my case, those are not needed. But the architecture code needs to express the right thing.
Yeah. And for the latter question, you mean test platforms or access to some test environment? I believe Longsong is happy to provide that, and we can help arrange it after the meeting.
Thank you.
Yeah.
Arnold writes to the chat that supporting multiple syscall APIs for old and new world seems entirely possible, and he's ready to help figuring it out how. Still, he would suggest not upstreaming that patch, but instead keeping it as a node patch for the all the binaries.
How do I see the chat in this? So, chat. Okay.
But I think we're running out of time, and we are out for the next. So
just
you
quickly
can connect to this.
Yeah. Supporting multiple syscall APIs for old world and new world seems entirely possible. Still suggest not upstreaming that patch, but instead keeping it as add-on patch that only gets applied to users that still need old world binaries. Yeah, sure. And I think first of all, we could continue this discussion after the meeting on the mailing lists. And yeah, I agree on not upstreaming that, but depending on the communication between us, the community, and closed source vendors, this problem might simply go away. So we don't have to care. Yeah.
I think we'll have to cut it here. So the next talk is about EFI and Elias.
Yeah, you got to stand there in the sit.
Who gets one point?
No, yeah.
We have this one and we have this one. Extending my support. This is you. So the arrows work or mouse works.
Okay.
Whichever you like. Need to track this. Yeah. And throw them at people.
Is Daniel here? Because we're basically, it's basically a wine about grab.
Okay. Good afternoon, everyone. My name is Art Biesheuvel. I'm currently working for Google. I was at ARM, therefore before, and at Linaro. Elias is also on the slide. He's in the front here. We collaborate on some of the stuff that I'll be mentioning in these slides. So I maintain the Linux EFI subsystem, so the EFI part inside the Linux kernel, and I also maintain parts of OVMF, parts of ARM support in Tiano Core, which is the reference implementation of the firmware side of EFI. Elias is at Linaro.
And in the U-boot EFI.
Yes, he works on EFI implementation, not the Tiano Core one, but the U-boot one, which is like an alternative firmware side implementation of EFI. So I've been asked to give a bit of a status update to what's happening with EFI, has been happening with EFI recently. And actually, most of the EFI discussions that are going on the list for OVMF, they're about confidential computing, which is covered in many different places, even at this conference, at KVM Forum, which is on the other side of town. I'm not really going to cover any of that. I should mention it because it's what I'm presenting is only a small part of the EFI work that's actually relevant at this moment. What I want to talk about is having EFI support as generically as possible, not have ARC-specific hacks in any of the layers. The confidential compute stuff is necessarily very ARC-specific at the moment, and even though there are some parts and some discussions, and I'm trying for OVMF to have the least amount of ARC-specific hacks. At this point, it doesn't really make sense to cover that area. So this is about the EFI boot flow. So I'm not talking about runtime stuff, but really about how you get from the firmware to loading the OS. So this is basically how the specification defines it. So either you're running in the firmware, and then you have abstractions to talk to the network, to the storage, load image, start image, do all those kinds of things. Then there's the conceptual OS loader, which is actually defined in the EFI specification that calls exit boot services, which means, okay, the firmware now goes away. And at that point, the OS loader is in complete charge of the platform and can do whatever it wants with page tables, memory, etc., etc. But yeah, the OS loader is conceptually different from the OS kernel, and there needs to be some kind of API because they're two different components. So there's an architecture OS specific kind of handover protocol between the OS loader and the OS kernel. And this is basically what Itanium implements in Linux. So there's no EFI stub or anything that fulfills the OS loader role. That's kind of out of scope for the kernel support. It's just the last block in this diagram, which means that necessarily there's some kind of specification, there's some kind of agreement on how these components talk to each other. So on x86, this was way before I was involved, but they worked around this requirement for a defined API between the OS loader and the OS kernel by just making it the same thing. So it means that the firmware calls once, as long as you're still running in the firmware, you use the EFI abstractions, you use the boot services as intended, and then the OS loader is the EFI sub. This is the component that calls exit boot services, and then it does its internal handling to branch into the kernel itself. And because it's basically the same binary, you don't need to define this internal API. It's just whatever this thing does to talk to itself is what the API is. So for x86, this is based on the legacy boot stuff. So there's a very interesting read in boot.rst in the documentation x86 directory, where you can basically make an archaeological journey through the history of Linux, booting from a floppy and all these kinds of things. Basically, that stuff is all there, and it's basically what the EFI stub uses to boot the decompressor in this case. So not even the actual kernel, but what the legacy x86 boot protocol defines as the first stage. There are a couple of limitations with the EFI stub approach. One being that the loading of an init.rd, if it's not done by the bootloader, it's done by the stub itself. So you pass the name of the file to the stub, and then the stub goes looking for that file through the file systems. But actually, it can only access the conceptual EFI volume that the image itself was loaded from, which is kind of deviates from what Grub and Lilo and those things were already doing at the time. So this was fixed. So one way of fixing this that the distro people implemented for x86 is to say, okay, we'll have a new protocol, EFI handover protocol. So while we're still running in the boot services and are supposed to run the EFI, use the EFI abstractions for loading a starting image, Rob will use load image to load the image. It will set up this struct boot params, x86 Linux specific stuff to actually communicate where the init.rd is. And then instead of calling start image, it will just branch to where it thinks the entry point of the image is and pass one additional parameter. And yeah, off you go. So this kind of works, but yeah, it violates the specification, it violates the layering and the abstraction, so it's not great, and over time it's becoming more and more problematic. So there's one other reason that I didn't put on the slides, but one other reason that x86 needs this is for mixed mode. So running the x86 64-bit kernel on an x86 64-bit capable CPU, but one that was booted using 32-bit firmware. And this is a very x86 specific problem. We don't have that problem on any other architecture. And for the same reason, well, actually the problem here is that load image works, but start image doesn't. So there needs to be a different way to evoke that image. So one problem with not using start image, it's like the first kind of symptom that something is not entirely right, is that a boot service like exit, which does like basically does a long jump back to the caller of the entry point, this stops working because start image does some things under the hood that no longer happen. So yeah, I'll get to that later. Yeah, so another issue with this is that Grub already knows this x86 boot protocol. So it knows how to reason about, oh, this image needs it init ID below 4 GB, or this image does not, or the command line needs to be there in memory, or there are lots of crazy rules and things that Grub already implemented, but which are necessarily now done by Grub, even though it's pretending to do an EFI boot. Gets worse. So there's the shim. And basically the problem that shim solves is also very x86 specific. So Linux wants to run on x86 PCs. x86 PCs are built to run Windows. The vendors don't care about EFI. They only care about what Microsoft tells them to care about, and then they'll get their Windows sticker and it's all fine. And actually the easiest way to comply with the secure boot requirements is just to only ever accept Microsoft certificates and not remove the ability to disable secure boot or enroll your own certificates. I wasn't involved in the discussions at the time, but I think one of the issues with signing Grub was that it's GPL v3. And generally, it makes sense to have like a separate shim, like a stepping stone that you collaborate on with Microsoft and not necessarily put that into Grub. So from the point of view of solving this particular problem, it's understandable how we ended up in the situation that we ended up with. But yeah, it's not great. And it's x86 specific, so we prefer to avoid it on other architectures. Yeah, so this is basically what we ended up with. So there are basically three different internal APIs now. So there's the one between shim and Grub, there's the one between Grub and the OS loader, and there's the one between the OS loader and the actual kernel. So the one on the right is kind of fine because that's after exit boot services, and what the EFI spec defines as being appropriate for doing whatever the hell you want. But the other two, they're basically violating the EFI specification by just putting stuff in memory and branching to it instead of using the proper abstractions. So load image, there's a difference between loading an image and copying something into memory, especially with peak of, it's like ELF, it has described sections which have a file offset and a memory offset. And it means you have to use the peak of header to construct the image in memory. It's not a one-to-one mapping in principle, even though the EFI stub kernel usually is. We're running into issues where the number of pages allocated needs to be bigger than the size of the image. There's a BSS section that needs zeroing. You need ICAS maintenance to ensure that the code that you put into memory is also executable via the iSight before you try to run it. So rolling your own load image, it results in lots of issues that we've having to have work around. So for the shim Grub side, it's even a bit more hairy because it's like works two ways. So shim exposes a protocol, and Grub calls that protocol, and then shim also uses load image, I think, or it might, but it also has its own version. It also hooks the existing one in the system table, so when the other image calls load image, it actually calls shim's version. And the result is that
basically, and if you want any of these components on a distro, you need all of them. And this is what, Ben, for instance.
And all the parts are distro specific, right? Every distro has its own. And every distro has its own grub patches. It's not.
Yeah, they generally have these like 200 out of 3 patches, and some of them are shared and some of them are different. But this is not upstream grub. This is really distro grub with lots and lots and lots of changes.
I have a patch to fix the problem there, but I'll post it probably next week to the list as an RFC, because of course it is not the right thing to do, but it kind of solves the problem of requiring a shim for now. So I'll send it to the grub list probably next week when I'm back.
Awesome. And this solves the issue where so basically the problem that shim solves doesn't exist in cloud VM use cases or the use cases where we don't have the x86 PC problem, right? So shim, if the certificates that you want to authenticate against are already in the firmware, then grub should be able to authenticate against those directly. And this is what your patch fixes, right?
Yeah. Yes, but it does it in a convoluted way due to how grub structures its verifying thing. So we're still not properly doing load image, start image the way we should, because it's just a verifying hook that verifies the image by loading it from memory to memory. Right. Basically, long story short. It works. It does the job for now, but I don't think we should still have the general discussion. How can we do better? Can we just have shim hook load image and just rely on that and always use load image in grub? I mean, there's a whole conversation here that needs to be had to do something better.
So one thing I didn't mention here, load image is also, and this is actually like defined in the TCG spec, like the trusted computing spec, that load image is actually what under the hood will do the authentication, but also do the measurement into the TPM. Which means that if you're going to roll your own load image, then suddenly you have to reason about, does this need, am I on a platform that does measurement? What is the policy? And if it's just pure TCG measured boot for EFI as it is defined, then it's all fine. But now with confidential computing, we'll have 4 different ways of doing attestation and measurement. And now all of a sudden, load image has to be aware of, this could be DICE attestation. This could be DRTM. This could be. So basically, by violating the layers like this, we're opening a can of worms that really should be closed. Okay. Where am I going? Okay, yes. So some of the work that we've actually been doing, Elias and I, over the past, I think 2 years already, this like slow. Yeah. So the EFI handover protocol, we don't really need that. Mixed mode is not the problem on any other architecture. And actually I have a fix for mixed mode, but it's like fixed in OVMF and in the kernel. And, but for generic EFI, we don't even have to mention it. So what we did is just have a protocol, like the EFI way of exposing functionalities via protocol. So you just expose a protocol that gives you an init RD. So if you define this in the firmware, in the loader, or whatever stage runs before the kernel, the EFI stop, all it has to do is see if this protocol exists, and if it exists, call it. And then all these limitations about, I have to reason about where it can be loaded. I have to, know our specific rules about placement, etc. It goes away because it's the EFI step that actually allocates the memory and is in charge of handling it, and the protocol just gives you the contents. So this is in U-boot, in the EFI stop. The grub patches, after a long time, are now on their way in. I think systemd boot or systemd stub, one of the two, has an implementation for that. So this is basically And RISC-V doesn't even enable the initrd command line loader. It only
EDK2 has an implementation as well.
yes. Another thing we did, Elios did actually, was so the EFI stub, and this is actually something that occurred to me when I was in the confidential computing microconference this morning. So currently, we measure the initrd. If you use load file 2, we'll measure it into PCR9 if TCG protocols are available. We don't do that yet for the command line, and actually the TCG spec, strangely enough, doesn't reason about the command line or the load options, as EFI calls it, at all, which is kind of an oversight. But yeah, we'll be adding that soon. The only thing we have to take into account here is what I just said about different kinds of measurement for different kinds of confidential computing environments. So I'd really like the TCG protocols either to be implemented by all of those, so we can just call it and don't care about it, or have an alternative TCG Lite, TCG 3, whatever, that all those firmwares can implement in their own way, and then the EFI stuff.
Yeah, so basically this has to be a callback to the firmware. The stub has to call measure that, and the firmware needs to understand what am I measuring where.
Yes, exactly. So we'll tag it with, oh, this is initrd, this is a command line, but beyond that, it's up to the implementation to reason about it. Yeah, another thing I did recently that was inspired by the LoongArch stuff is have a basic EFI decompressor. I mean, ARM64 doesn't have a decompressor because basically you need to set up a completely different runtime, map the memory with cache attributes, do other things, run the decompressor. It's a bit, it's a lot of work for not a lot of gain. EFI, however, is a very high-level runtime already. So if you can just run an EFI app that decompresses something and load that using load image and start it using start image, yeah, basically all the ARC-specific stuff goes away. So this is send a V5 the other day, which enables this for ARM64, RISC-V, and LoongArch with maybe 5 lines of per arch code, and everything else is generic. Let's show. Wait. Yeah, so this is basically what we want, what I want, and what I think is the best for having generic EFI boot support. So the dotted lines are optional components. So if you install your distro and your distro installer notices that the distro certificate is already in the firmware, it doesn't even have to install shim. Or if you're not on x86, you don't have to install shim. And yeah, if you want zboot, you get zboot, but you can also remove it. It's all using the APIs as the spec defines them. I think that's all I had. Yes, that's all. Any questions?
Just throw.
Yeah.
So
when you're talking about new architectures, do you mean using UEFI on architectures we already support in Linux, or using it as the only boot protocol for architectures we don't yet support?
So are you asking if other existing architectures will gain EFI support, or should gain EFI support?
Yes, what your goal was, because there are not so many architectures we're still merging. I'm always saying, well, this might be the last one. There's probably 3 or 4 more.
I'm not necessarily reasoning about the future here, but more about why the motivation around some of the recent work and why it's important to keep things generic. And basically, the zboot stuff is a case in point where it's all generic code on the firmware directory, and
the Arch only needs to change its make file to actually wire it up. Yeah, I don't see. I mean, existing architectures that use something else. Yeah, yeah, it's up to them. Well, basically, I want this to be rooted in the spec, right? So the EFI spec doesn't have any other architectures, so I would expect those to be introduced first, so we can actually see whether what they're doing complies with the spec. But yeah, if people are interested in doing that, it's perfectly fine.
There was a question there.
Done. So what I was wondering is how coupled is setboot to the kernel image itself? Like, can you take setboot?
Sorry, I can't hear you. Can you talk more into the microphone, please?
Can you take setboot and apply it to an old kernel image and combine the two to make it work? Or does it depend on changes in the kernel itself as well?
I think you could backward the patches quite easily. It doesn't really rely on anything recent.
Yes, but without, is it possible without any backporting? So we build setboot, and then we combine it with an existing kernel image. Would that at all be possible?
Yeah, yeah. If you break out the patches and make a standalone thing out of it, you can easily compress any EFI app that you want. Yes. Ben?
So ZBoot just uses load image start image, right?
Yeah.
Which means, so on the wrong architecture, you still have the shim problem.
Yes.
I know I saw you had some slide you skipped over about the whole hooking of load image and start image. I don't know if you maybe don't have time. Is there a path here to get rid of the shim lock protocol? Because fundamentally, even if we hook load and image and start image from the shim, we still have to do an implementation that does not call the real ones, because the real one won't be able to verify the image regardless, which kind of defeats, which kind of brings us back to the same problem where the real load image and the real start image that might do some magic we don't know about are still going to be skipped. So I mean,
the fundamental.
and sorry, just to finish, and do we think we have the ability maybe to work with UEFI to solve that in the long term by actually adding a mechanism or a way to register protocol with UEFI for alternate type of verification, or I mean, whatever mechanism we can think of that is reasonably safe?
Yeah. So first of all of this runs privileged, right?
Yes.
So even if even before whatever stage is running calls exit boot services, it's in complete control of the platform. You can change mappings, do things with interrupts, anything it wants. So it means that loading an image and getting like an authentication violation back, does it really help to prevent that image from being executed?
Sure, but as when we discussed that yesterday, if load image internally fails, it might not do things like, I don't know, cache management or something that might be needed. So we still end up in this gray area, and we still end up outside of the spec, and we still end up.
It's not entirely like that. So load image, its documented behavior when it returns an access violation is that the image is not unloaded. So for every other error that occurs, the image is never loaded and you don't get a handle or anything. For this particular error code, it says, okay, the image is, you get a security violation, but the image, the handle is valid, the image is there.
Okay.
So basically, because whatever is running could still execute or do whatever it wants, does it really help to prevent the start image call from succeeding on that?
As long as the implementation of UEFI doesn't do something that causes start image to fail in that case. Okay, fair enough. I would still love to see things spelled out in a spec so that enables us to do these things in a way that we know is solid, we know is going to work down the line. Well, at the moment, we're kind of playing a little bit with fire, and we have those assumptions baked in, which is not great.
Yeah, no, I agree.
So we are on time. And the next to present
is Goran. Go, can you turn? Go, can you turn please your camera on? And I made you present, so I see a presentation already there.
Yeah, yeah. Okay. Can you hear me?
We hear you. Yes.
Okay, great.
So, and we see you. All right.
It's my turn. My name is okay. My name is Goran, and come from Alibaba, and I'm a kernel CPU subsystem developer. And today I want to talk about load reserve store condition architecture forward progress guarantee. This word is come from the RISC-V and other architectures such as ARM called it load exclusive, store exclusive, and some architecture call it load link. So they are the same. They are the same. Okay. The background first I will introduce the background. The motivation I do this is I have pushed I want to push the queen spin lock to RISC-V, and this work is released in the 2019. Yeah. And as we all know, queen spin lock is competent in both in the embedded system or the cloud server. It solves the fairness and cache line bouncing problems and ensures performance and size. So it's very valuable function in the kernel. We start work in the 2019, and the version 1 is made by the Michael Clark. Yeah. And this code borrowed from the MIPS and just wrapped by the compare exchange. And in the version 2, I directly used the assembly code to implement the compare exchange section. And that's the code is not perfect, but it's correct. I think I have reviewed that. Yeah. And then some small fix up and coding conversion in the version 4. We the end find that in the Q spin lock core code has the native compare exchange implementation for the exchange type. But this patch is rejected by the maintainer. Yeah, I would explain why. That's really correct. And in the version 4, it's very valuable thread. We talked a lot and discussed a lot. Most of the materials in this presentation from this thread. And then we take the advice from the Peter Jr. and we try to implement the take log. And I send assembly code, but Peter Jr. gave a generic version, and which have merged into the mainline by the power. And RISC-V, OpenRISC, LoongArch are using it now. And in version 5 this year, I pick up the patch again and continue push to spin lock for the RISC-V and give the clarification of the requirements in the Q spin lock. Yeah. And in the version 7, I give out a combo lock implementation to combine take lock and Q spin lock in one image. And in the 9, I involved more architectures who want to Q spin lock that together and have more discussion on it. So that's the background. Yeah. And I put the old link here, and if you have interesting, you can have a look. So, and today is today's agenda. Yeah. firstly, I would talk about atomic instruction category concepts. Yeah. And the second, I would give the forward progress guarantee concepts, and then XM memory model and how we find the forward guarantee in XM memory model. Yeah. And and then I will show some microarchitecture implementation cases. And then we talk about take lot, queen lock requirements, and in the end we give the architecture summary. Okay. So so let's talk about the atomic instruction category. Actually, we can separate the atomic instruction in two parts. Yeah, one is pure AMO instructions. That means one instruction do all the read, modify, and write back only in one instruction. So so we call it the AMO instructions. Yeah, and another is the load reserve store conditional. Yeah, that means the OMO instructions code composed by the load reserve store condition, and include all of the atomic op, fetch op, and return exchange, compare exchanges, even a compare exchange down. Yeah, I will show you how to do that in the later slide. Yeah. And so that means we have two kind of atomic. Yeah, one is pure AMO instruction. One is the pure load reserve store condition architecture. Yeah. The pure load reserve store condition, we can the architecture is the such as the ARM32, Sysky, OpenRISC, and the pure AMO such as the x86, and the ARM64 is the pure load reserve store condition, all the pure MO. They have called it LSE, large system extension. When you use the large system extension, you will move to all the atomic instructions. And another architecture is a little bit confused. They mix the MO and load reserve store condition. That means part of the they give out some MO instructions, but they don't give the complex one, such as the compare exchange. This kind of RISC-V and LoongArch is the case. Yeah. And why we need a load reserve store condition? Yeah, because the atomic instructions come out first, and this one is come later. And here I put the RISC-V comment up here. Actually, I conclude the right side into the left side. It have give the four advantages. That's the CS has the ABA problem, and the CS is expensive, and the DCS is more expensive, and the load reserve store condition semantic is more efficient than the CS. Yeah, and he also gave the two disadvantage of the load reserve store condition. That's it says it's what calls live log more than the CS, and DCS is basically primitive in the software ecosystem. And in the end, he also mentioned about the transaction. I don't know why this comment mentioned the transactional memory model here. And so to that means because RISC-V didn't give out the multi-word load reserve store condition instructions, so he said we hope the transactional would help. Yeah, but it's not related to the forward guarantee because it's weak forward guarantee, and you still need to prepare the traditional atomic instructions pegs for retry of the transactional. Yeah. All the comments here is so subjective. Yeah, it's so subjective description, and the The only I agree is that CAS is expensive, yeah, and the load reserve stock condition is really cheap, yeah, really cheap. Why? Because the real world is belong to the atomic instructions, yeah, and we all use the load reserve stock condition to implement atomic. That's the truth. So there is no load reserve stock condition schematic in our Linux or in our software ecosystem. I don't find that. Maybe you can argue me. Okay.
I have to say,
okay.
I have to say, I would disagree with the line that CAS is expensive. That is entirely an implementation detail.
Especially if all you're doing.
But sorry, I'm just saying on other architectures, it is significantly cheaper than load link store conditional for many common operations.
Especially if all we're doing is CAS with load link store conditional anyway, right? Like it's not any cheaper. It's the same thing. It's just.
Actually, it have said here, if you implement the CS, you need the register field. I mean, your microarchitectures prepared a large register field, more port, more import. You need 3 import and 2 output. So that would increase your hardware implementation cost.
I think what you're saying here is it's more expensive to build the hardware, not that the operation is more expensive in practice as a user. That's a very
okay. Here what I mean is the CS is expensive in hardware implementation, not the operation is expensive. Yeah. Actually the operation LIC operation is more expensive. I mean, yeah. Okay. So here is it. And here I would say what is for the progress guarantee, yeah, and there are 2 concepts of the for the guarantee. First, we use the load reserve stock condition to implement atomic. So we hope the atomic would have a strong for the guarantee, and then it will behave like atomic. The forward progress guarantee means strict forward guarantee. I means maybe the only local events code failed stock condition, not the cat concurrency cannot disturb it. So it's one concept. That means the stock condition should not fail. I mean, should not fail. Or mostly success. Yeah. And the second is called the CS loop for the guarantee. Yeah, that means if you write code, this code is come from the Q-Spinlock exchange tile implementation. One CPU course is massive, and look here, if you have the CS loop for guarantee, and this loop cannot infinitely loop. Just a two times loop would be broke. Yeah, a second loop always breaks without local events. Yeah, that is 2 concepts for the guarantee. One LRC and one is compare exchange. Yeah, to prevent the leave loop. Okay.
Can I just check with you're defining these as properties, but my understanding is that basically no hardware on the planet provides that first guarantee.
The hardware need to give the guarantee of that. Yeah, LRC and CS loop for guarantee. I will talk later. Yeah. Okay. So here is here is the concept of what the forward progress guarantee is. We need not only for the load reserve stock condition, but also for the compare exchange. Yeah. Okay. Okay. So how we measurement it, how we found which machines is for the guarantee, could have the for the guarantee. So we move eye on the XM memory model. Firstly, I look at the LKMM and his role is per here, and the litmus cases is here, and there is no LIC primitive found. So they all are high-level abstractions. So I cannot get view from the kernel memory model to see how forward guarantee is in a machine. Yeah, and so I don't know would the kernel would prepare the this kind of the semantics. I don't know, but now, yeah, but
so sorry,
now
again,
there's
just to be
no-
clear, the CAP model and that language does not at all describe forward progress guarantee in any way. All it provides is reachable states. So the abstraction does not provide that at all.
Yeah. Okay. Yeah. The memory model. Yeah. The Hertz-7. The Hertz-7 give out a lot of states, and you can run it on the machine and see what happening, what's the states, what got. So what I say here is that there is no this kind of semantics I can reference. Yeah, but I can find that in the ISA XM memory model. Yeah, and I choose a simple one. Is the script load resolve documentation for. Yeah, actually, memory model is a very large topic today. We don't talk more about the memory model. We just talk the forward guarantee, very small part of it, and we just utilize the litmus tool to see how the forward guarantee is. Yeah, here is the test case I got. Yeah. And you would see there were two cores, two threads, and one often execute the load resolve documentation, and we can run it on different machines and see how documentation field is. Yeah, and that means how the register 8 x8 be non-zero, be 1. Yeah. And this XM memory model is confounded. This is fine. Yeah. Okay. So firstly, I run it not my run. I just find a log. Yeah, that's on GitHub from the U5010. It's a real machine. Yeah, and you will find the field. The field is very limited. The field is very limited, and the only millions field. I mean, only millions field we have written a lot of times. Yeah, but only very less numbers case status found. This that is. Yeah. So most of it is success in this machine. So from this result, I would say, oh, this machine is a strong forward progress guarantee. Yeah, it's not weak, it's strong. Okay.
Just as nomenclature here, strong forward progress means an absolute guarantee. I don't think you're saying this is an absolute guarantee because testing cannot prove that. But it's absolutely, it looks very good, but I don't think you have a strong forward progress guarantee. There's a technical term.
I don't think it's the absolute forward guarantee. I mean, we still could let it field. For example, if the local events such as the traps exception could still disturb it. Yeah, I mean, strict forward guarantee, strong forward guarantee, maybe just the P1 cannot disturb the P0. Of course, you see from the test result, I cannot say there is no remote events. Yeah, because we only see the numbers of that. We don't know the reason of that. Is that right? Yeah. Okay. But I ran the same test on the Qmu. Yeah, on the Qmu. the Qmu implementation is not correct because the Qmu using the CAS implement load reserve stock condition. When it's translated to it. So actually, I think I thought the Qmu should be weak forward guarantee, but the result is it's just 100 times weaker. Yeah, than the 540. Yeah. So it's not so weak. Yeah, but I think it's not. It's because the Qmu is executed so sequentially. Yeah, and
sorry
actually,
to interrupt. Just one question. So I was under the impression that in order to provide guarantee about forward progress, you had to model your system, or at least let's say the monitor that would be checking for the link load store conditional collisions, and then run a model checker with forward guarantee progress checks on that model. So I don't think this is part of what is being checked here. Am I correct?
Yeah, like the HUD tools, if you run it on the axiomatic model, it shows you the reachable states and it will absolutely show that these can fail. Right? That means you do not have a strong forward progress guarantee. Absolutely. All that it's checking is the reachable states. It's not giving any guarantees of forward progress.
But we can, I mean, we can see how many stock condition could fail in this scenario, in this litmus test. I know this litmus test didn't give out the states how states is. I mean, what I just utilized this litmus test to show how the forward guarantee would behave. Yeah, we just easily count how many stock condition failed is. Yeah. So if you want to see what the machine for the guarantee is, that's I found a way of that, and you can disagree with that, but I just show you different results in different machine. Is yeah. If you run this litmus test on some weak for the guarantee machines, you will find maybe higher percent of fail. Yeah. Okay. And then I modified the litmus test and let it more failed. That means here is what I have done. I just let P1 more frequency restore, yeah, on Qmu, and then the stock condition could failed more 100 times, yeah, more 100 times weaker. Yeah, that means not only the hardware could let the conditional failed a lot. The scenario, the usage, how you using the load reserve would also could failed. I mean, could also relate to how failed it could be. Yeah. So here is what I want to show you, the forward guarantee results. Yeah, how to measure it. Okay. Okay. So let's talk about how we implement the load reserve stock condition. The most famous implementation is come from the ARM 32. It's called the exclusive monitor, and an exclusive monitor is a simple state machine with the possible states open and exclusive. A lot of exclusive operation updates the monitors to exclusive state. A store exclusive operation access the monitors to implement whether it can complete successfully. A store exclusive can succeed only if all accessed exclusive monitors are in the exclusive state. So that means it's a weak forward guarantee implementation. That means it permits the remote thread could catch concurrency protocol could disturb the load resolve store condition peer, and that means remote events could fail the store condition, and the right side is the I found a patch to fix to enhance the forward guarantee, and they using the prefetch catch line prefetch instructions and make it store condition continuous.
Just to be clear, that's not a guarantee. That's an optimization.
Yeah, that's automation. Yeah. Okay, I had 5 minutes. I need faster. And then microarchitecture case. Here is another implementation come from the Dangshan, and which referenced by the boom. Yeah, and it's using the locked catch implementation, and I think it's very strong for the guarantees. Yeah, and that means it's have the lock cycles and back off cycles, and in the lock cycles, load resource documentation in peer in this cycles cannot disturbed by the remote events, but it could still receive the local events, and so it's have a very strong forward guarantee, and when the store condition finished, and some back off to prevent some malicious hearts to block the whole system, and next is the compare change loop forward guarantees, and in this implementation, because the compare change we can call we can think it is the load reserve store condition peer, and in the log cycles we can contain the two of them, but we still let the third out of it and back of it, yeah, and give the back off between them, and then in this CS loop and in the signal loop, they would be in the same log cycles, and then the forward guarantee would be guaranteed. Okay, and another microarchitecture optimization of the forward guarantee is atomic map. It's a little bit the rock. I think it's a little bit of rock technology because it makes RISC machine works like CISC. That means you can using the macro OP fusion, or we call it instructions fusion, and wrap this instruction into one macro MO operations such as the load reserve, and then you can mapping these atomic operations to the interconnect transaction. Yeah. The trajectory with atomic store, atomic log, atomic swap, and more complex is atomic compare. Yeah. Another word is some interconnect cannot support this trajectory, and some interconnect could support part of them, but the compare exchange is so complex, so this kind of interconnect cannot support it. So maybe that's why load reserve store connection is more flexible. And in this scenario, actually, they are the same. Yeah, actually the load reserve token is the same with atomic. Yeah.
So I think you have 1 minute left.
Okay. And so one correction is about some people say the so the load link store condition architecture cannot give good for the guarantee, but I think it could. That depends on what the microarchitecture could do. Yeah.
The problem here is that it doesn't matter what a microarchitecture does. If there is any implementation which does not do that, the architecture does not provide the guarantee. And the key detail is that no architecture provides this guarantee today.
Actually, some architectures make it very flexible. That means you can implement with a straightforward guarantee, but you can implement with the weak forward guarantee. And and that's why this kind of architectures need take lock or the Q spin lock, because they have the compare exchange. They have the exchange. They have the swap atomic swap instructions to meet the requirements from take lock, but they don't. But in the ISA design, but for the Q spin lock mixed atomic exchange, they need a micro architecture support. Yeah.
Go, we are running out of time. I'm sorry to interrupt you right here, but that's all time we've got. Thank you very much for the presentation. Thank you very much for everybody who attended. And now we should run downstairs before the eat our lunch.
And thanks to Mike and Arne for organizing the micro conference.
Thanks, Arne, for attending remotely. And see you next year.
It's been going on for years.